So now we're going to go over another carbon nucleophile, which is a new carbon nucleophile that a lot of you probably haven't seen. And it's with this new carbon nucleophile, we're going to do a reaction called the Wittig reaction. In the Wittig reaction, what happens is you take an aldehyde or a ketone, and you react it with a carbon nucleophile shown here. And we'll go over a little more about this carbon nucleophile and where it comes from. But essentially, this is still a carbon nucleophile. This carbon has a negative charge on it. And what you end up doing is you do end up doing something really interesting in this reaction and super useful. You take an aldehyde and ketone and you convert it to an alkene. But you do it in such a way that you don't just do an elimination reaction, you actually make an alkene in such a way that you're making the molecule more complex by adding a new carbon onto the molecule, because what you're doing is you're adding this carbon nucleophile to that carbonyl carbon. Now let's talk a little bit about where this carbon nucleophile is and what this really is. Now, you might be thinking of like, this looks like a really weird molecule, and it is a really interesting kind of weird molecule. This is called the Wittig reagent, and the Wittig reagent is something that we call a phosphorus ylide. So in the phosphorus ylide, what happens here is you have a formal negative charge. This resonance structure turns out to be super important and super useful in kind of thinking about what the phosphorus ylide looks like. And an ylide is a molecule that's a neutral molecule, but it contains a negatively charged atom adjacent to a positively charged heteroatom. And so we have that situation here. So this is really nice because even though this form of the ylide, this resonance structure of the ylide, has the carbon having all of its octet filled, um, and what happens here, if you think about it, the phosphorus has expanded its octet, which phosphorus can do, but it's actually nicer to think about the phosphorus being in this situation here. The overlap between the carbon and the phosphorus isn't all that great to make a pi bond. And so when you have this phosphorus ylide, what probably happens in this mechanism is that there's a 2+2 cycloaddition that takes place between the ylide and the aldehyde or ketone. So the way this would look like, if you think about the carbon being nucleophilic here, that's going to attack this electrophilic carbon, and then as this attacks, these electrons are going to kick up and attack the positively charged phosphorus in a 2+2 cycloaddition. Now this makes an oxaphosphatine. It's a four-membered ring. We know four-membered rings aren't super stable, so then there's a fragmentation that happens. So this bond is going to break, and then this bond is going to break to make your CC double bond. And you notice that you make your new carbon-carbon double bond, and you make something known as triphenylphosphine oxide, which is a super stable byproduct, and this really helps drive the reaction forward. And in fact, this triphenylphosphine oxide is such a pain to get rid of, but it helps the reaction go all the way to the desired product. Now, where this phosphorus ylide comes from is it comes from the reaction of a phosphorus nucleophile, triphenylphosphine, an SN2 reaction on an alkyl halide, followed by an elimination of that of the salt you make here. So the first step is you take a triphenylphosphine, react it with an alkyl halide. This makes something that we call a phosphonium salt. This is shelf-stable, so you could make this and store it. And then when you're ready to do the Wittig reaction, what you would do is you would take this phosphonium salt and react it with a very, very strong base. Something known as N-butyllithium would be an example of a very strong base. So this is another organometallic compound related to the Grignard reagent. The major difference here is that instead of having a magnesium here, you have a lithium here, but it's still an organometallic reagent with a negative charge on the carbon. Super, super basic. So that negatively charged carbon is going to remove a proton of this phosphonium salt and kick these electrons up to make the Wittig reagent. So because of this first step is an SN2 reaction, it's usually this phosphonium salt is easiest if this molecule here, if the alkyl halide is either a methyl halide or primary halide. You can get away with doing it with secondary halides, but it's easiest if you have the primary or the methyl halide. Now, what's interesting about the Wittig reactions is that the Wittig reaction as it's drawn is stereoselective. If I take if I take an aldehyde or a ketone and I react it with my phosphonium, the ylide here, I generally favor the Z alkene for that molecule. This looks a little weird in the sense that this isn't the most stable alkene, obviously. The E alkene or the trans alkene in this case would be the most stable. But because of the way the reaction takes place, for a normal Wittig reaction, the Z alkene is favored. Now, you can start to favor the E alkene, the trans alkene, if you start to have electron withdrawing groups on the Wittig reagent. So whenever I put electron withdrawing groups in the form of like something like an ester or an aromatic ring, I start to favor the E double bond. And furthermore, I can do the reaction with something called, I can do the Horner-Wadsworth-Emmons reaction. This employs a reagent similar to a stabilized Wittig, but it looks a little bit different. And here you're going to be making a double bond here, and this is also going to favor the E alkene as the major product. So when you do the Horner-Wadsworth-Emmons reaction, so this is the Horner-Wadsworth-Emmons variation of the Wittig reaction, and you see here that you have the E alkene here, the trans, in this case, alkene. And the choice of solvent and the use of Lewis acids can also affect the stereoselectivity of the Wittig and the Horner-Wadsworth-Emmons reactions. Turns out that these reactions are super useful, and you can do a lot of really interesting things with these reactions. And because you're making these, because these ylides can come from, and these ylides can come from much more complex molecules. So you can actually couple two pretty big fragments together via this reaction. Now, one of the things we want to think about is now that we realize we now have a new way to make alkenes that goes beyond just the elimination reaction. So when you see an alkene retrosynthetically, one of the routes you have to be thinking about is doing a Wittig reaction to make that alkene. Now, when you have an alkene such as this, there are technically two Wittig reactions you could do to get to that alkene. I could use this carbon as the Wittig reagent, right? And I could use this carbon as the carbonyl, or I could use these carbons as the Wittig reagent and this carbon as the carbonyl. And to figure out which route you want to do, you kind of have to think about which is going to be the best way to make the Wittig reagent. Now, if you think about it, to make the Wittig reagent of this route here, of route 1, what you would have to do is you would take a methyl halide, react it with triphenylphosphine, followed by base. Or if I want to make the Wittig reagent in route 2, I would take this secondary halide, react it with triphenylphosphine, followed by base. Because this is using a methyl halide in the SN2 reaction, route 1 is going to be better. So overall, the way this is going to look like to make this the best way to make this particular alkene is to take methyl iodide, react it with triphenylphosphine in an SN2 reaction. I'll do an elimination reaction to make your phosphorus ylide, then react that with your carbonyl compound in a 2+2 cycloaddition followed by fragmentation, the Wittig reaction, to make your alkene. So that's all for the Wittig reaction and the Horner-Wadsworth-Emmons reaction. Let me know if you have any questions. Thanks, and I will talk to you later.